So can you hear me?
Yes, I can.
Okay, perfect. And I should put you a bit louder. Everyone can hear you. Okay, so let's start.
Maybe you should send the link into the chat, because on the previous lecture, I thought it isn't translating because there is no link in the chat.
And well, the link is in Wikipedia.
Yes, but
yeah, but I can also put the YouTube link on the chat. Okay, where else? Now I need to find the chat. Okay. Yes, so today I will speak about a more realistic setting for machine learning, which is called agnostic setting. Previously, first. Okay, so previously we spoke about a realizable setting. What does it mean? It means that when we assign labels for training and testing, we need to be consistent with some function in our hypothesis class H. But for machine learning, it's not a good setting for two reasons. So first, there can be, the true function can be pretty complicated. And there is no chance that you can train with a limited amount of data, a model that can capture all complexities. Okay, nowadays people work with like pre-trained models and such things. It's a different story. But if you train from scratch, it's often the case. For example, if you're training on a rare language, there is no chance to capture all nuances. But there is a second reason, like there might be an inherent randomness inside the problem. For example, a part of a picture is hidden, and somebody throws a random coin, and sometimes you need to see the size of the coin with your program, but sometimes most of the coin is hidden, and so then you cannot do better than random guessing. So there is a natural thing. So you can not assume that some function in H will be consistent with all training data or testing data. Okay, so plan for this lecture, I will explain what is this agnostic setting, and then I will go through a bunch of easy lemmas and observations. So I will say what is risk, what is empirical risk. So empirical risk is just error on the training set. This is expected error on the test set. And then after a bunch of simple observations, I will prove this theorem, which says that if our hypothesis class has small VC dimension, then the error on the training set is representative for the error on the test set. So that's our plan. But before I do, I will repeat something from a few things from measure concentration. So you will do a bit more in one of the exercises of the seminar. So what are concentration inequalities? So these are inequalities that says that a random variable is likely to be close to its expected value. And so it says that either x minus expected value of x is at most something or at least something. And here, hopefully, some small quantity. And they are almost always proven using Markov inequality. So in the last step, you will apply Markov inequality after a bunch of manipulations. And we can say even a bit more. These inequalities will typically start with saying that absolute value is bigger than some t. So we will set value of y equal to, so y will be a function of absolute value of difference of x and its expected value. So then we apply Markov inequality to this y. So f is monotone function. We apply Markov inequality to this y, and then we obtain this result. And so famous example is Chebyshev inequality, but maybe you already know this from statistics course. And so do you remember what is the function for Chebyshev inequality? What is f?
Just square x minus expectation of x.
Yeah.
And t. The two square both sides of this inequality is like that.
Yeah. So this f is just the square of this value. So we take this, we consider square of absolute value, and the expectation of this square is precisely the variance, because absolute values, they drop because if it's negative, it becomes positive. So there are this works nicely. So here is Chebyshev inequality, and another famous example is law of large numbers. I think this is weak law of large number. I forgot a little bit. So how is this one proven?
Using
Yeah. But
just look on variance.
This limit is equal to 0. I forgot to it. Yeah. So we look to the variance of sum, and then we say variance of x1 plus xn is equal to variance of x1. This is not true. So how should it be correct? Multiplied by n. Yes. And then if I divide by 1 over n here, I need to divide this variance
by n squared.
Yeah, 1 over n squared. And so here to prove it, we just apply Chebyshev. So we consider the variable that's this mean here. This will be our x when we apply Chebyshev. And we know that the variance is x divided by n. And so when we set t equal to epsilon, then we get something that for each fixed epsilon. So we will have variance of x1, and here we have 1 over epsilon squared. And so for each fixed epsilon, so we fix epsilon and then take a large n, this will be equal to 0, this probability. Well, that's how it's proven. And another example is Hoeffding inequality. So have you learned the proof already?
Yes.
Yeah, and so what is f for Hoeffding inequality? Yeah, indeed, exponent. And then we have to look to the expected value. So when we apply this, we need to look to expected value. So well, it's a bit more difficult. So f is so here we will have f of t equal to exponent by r times t, where r is some parameter that we select in the end of the proof. We will optimize our bound, and then we have r equal to like 4 epsilon will be chosen, and then we need to look to this expected value, fx minus expected value of x. So we have to look to exponent of r times. So we look at. So well, here we don't apply absolute values. So we run 2 times to the proof for each side of the inequality. So so it's a slight lie I made, but okay. What hell is the matter? And how can we bound this inequality? How do we do it?
We do some tricks with measure. We did some tricks with measure on statistics course.
Yeah, you learned a dirty proof in your statistics course. And I gave you a nicer, you did something, okay. I mean, just, I don't check your statistics course, but I know in 95% of courses, you learn a long dirty proof to show that this is small. But the statement that this is small is a lemma we've used already many times. It's in the homework. No, maybe not in homework, but at least in the seminar. Well, this is Hövding inequality. The thing here is Hövding lemma. And that says that this is bounded by exponent. Okay, so here we have variables that are inside unit interval. And for variables inside unit interval, this is bounded by r squared over a. So what we have here, so to prove this. So let me rewrite it a little bit so that it becomes easier. Like this. So we have z minus exponent z smaller than epsilon. Oh, it's already done here. We don't need this. We can just evaluate this thing directly. For the top, we already have the bound. This is bounded by exponent. So we will apply this for each variable. Z1, expected value of Z1. So this will be expected value of r squared over 8 times expected value over r squared 8. So here it's n times because sorry, what am I saying here? No, I'm saying nonsense here. I mean, we need to. So z is equal to the sum, right? And this will be I studied this so many times and that now I
can tell how Kelvin lemma implies first inequality, because on statistics we had Kelvin lemma but we did some tricks with measure to
to prove this, but it's just Hövding lemma. So this is Hövding lemma is z belongs to unit interval, but now to get it inside unit interval, I need to scale it, and that means we have here n squared. Okay, but this is not what I remember. I think now if we compute something, there will be a problem. So this is bounded by exponent r squared n squared over a, and then here we divide by f of t. And so f of t. Oh, but now I have things here too. So here we have exponent of r epsilon n. Okay, it's not a problem. And so now we set r equal to 4 epsilon over n. Next. 4 epsilon times n. That also doesn't work. Okay, what did I do wrong? I remember I should apply Markov inequality. Okay, I see. It's with this absolute value, it's bothering me. So we are applying this form. Okay. And now we can say that this happens just n times. Why? So when we look to the exponent, it's a product of terms, and each term is bounded by one application of Hövding lemma. So I'm using that this is bounded by this, and so exponent of r z minus exponent of z. So z is the sum, is bounded by exponent r squared n over 8. And so here we don't have this n, and now things work. Because this is exponent of n times n r times r over 8 minus epsilon. So if you set r equal to 4 epsilon, then it's precisely what we want. It's equal to exponent of 4 epsilon n times no, doesn't work. Yeah, sorry, yes, it works. Yeah, 4 epsilon over 8 minus epsilon, so it becomes minus epsilon over 2. So this is exponent minus 2 epsilon squared, and so it's okay, it's precisely what you need. And then this Hövding lemma with this 1 over 8 can be proven very easily for symmetric variables. It's seminar exercise.
Okay, I remember that we had third semester
Yeah.
proving a Kelvin lemma, not proving this.
Ah, okay, yeah.
Okay, I looked, and we had a big proof of Kelvin lemma, and then a small.
Yeah, small
Application
proof of Hövding inequality. Yeah. Yeah, and I gave a proof some lectures ago with not 1/8, but 1/2 or something, or
It was somewhere near.
Yeah, in the
Johnson
beginning.
inequality.
Yeah. Okay, so it's really important for theoretical computer science or anything related to machine learning or whatever is the most important thing. It is strange that this exponential function is so fundamental for so many things to bound something. Okay, yes. So that's like a kind of technical overview. So let me delete everything. I will use Chebyshev inequality later, but I think I can safely remove it. And let's go back. To notation. So what is our model now? We will assume that P is a measure over inputs times outputs. And so we will directly sample input output pairs. So S will be a list in x times y to the power n. And then this, so now S is not a list over only inputs, but also input output pairs. And we don't need the true function anymore. So our model becomes easier. And so we will give
So
this
we can
as,
have several outputs for each input.
yeah, indeed. We can have the same input repeated with opposite labels. And our task is to predict as good as the best possible, as the best hypothesis class in H. So H remains the same. So it's a subset of x to the power y to the power x. Okay.
Is y still by one?
Y, yeah, y is still equal to 2. Just for this and next lecture, and well, for the course actually, y equals 2. That's not a bother with regression. Okay. Okay, sorry. Then
So
this
we
as
can give functions in our purposes class that output sometimes
No.
and sometimes 1 for the same x.
No. H is a subset of deterministic functions.
Okay.
Yeah. And we also assume that Fs is deterministic.
So our learning algorithm doesn't include any randomness.
Yeah. So we need to
What does-
prove this. Well, Fs. Fs is the, so we give S to the learner, and it outputs a
yeah,
classifier, yeah. Okay. And then we want to say to understand what is quality of Fs, and this is the risk. So, and I will now use a common notation. So we say that the risk of a function z, g is a classifier. So g goes from x to y. And so this will be just the probability when we pick pairs x of y, that g of x equals y. And then there exists a notion of empirical risk. And this depends on the training set or just any set here in S of G, and it's just a fraction of misclassified points. And sum over I smaller than n. So that n be the size. So let's just say that the size is equal to n. Then we have the indicator of G of x equals y.
People say that it's opposite not equal to.
Sorry, yeah, good point. Yeah, yeah, and here, yeah, also the risk is one. Okay. And so simple observation is that expected value. So when we fix a single function and generate a random set, Pn, then expected value of empirical risk. So let's call it test set, just for to avoid. So this is equal to the risk of G. So that's clear, right? Expected value. So if this sum, we take a bunch of independent inputs. So then this average will be just equal to the first.
Elements of P should not satisfy any additional conditions. That's just basically a pair of random input
And output, yeah. Okay, so then there is a special classifier called bias optimal classifier, which optimizes conditional probability of the label given the input. So bias optimal, so we say that G is bias optimal if probability of G of x not equal to y given x is at most 1/2 for all x in the input. And here we assume that conditional probability is defined. So x is in the support of marginal distribution. Okay, so let's do a simple example. I know it's a bit boring, but that's just for let us say that x has 3 values, +1, and y is 0 and 1. And then let's say 1/5 here, 0, 1/5 here, 0, 1/5, and 3/5. So what is risk of a bias optimal classifier in this example?
Shouldn't we just sum up to 1?
Good point. Of course, it should. Yeah. Okay. So now, question: what is the risk of a bias optimal classifier? Yeah, indeed. This clear. Okay, what will bias optimal classifier predict on -1? 0. So yeah, this is the error. Then this will be the error, and then this will be the error. So it's 1.
So it just predicts the most probable.
Yeah. So most probable, it will have probability at
Yes,
most.
okay.
And then there can be several values for some x. When it's exactly 1/2, you have 2 choices. Or when conditional probability doesn't exist, then also. Okay. We can define agnostic sample complexity, but it's not used so much. So what is our goal? As I already said, So agnostic sample complexity. So it's so let's call this N agnostic for a hypothesis class. Then again, there are two parameters, epsilon and delta. And we want, with probability 1 minus delta, obtain a classifier that is the most epsilon worse than the best classifier. So it is minimum n, for which there exists a learning algorithm such that probability that the risk of Fs is bigger than minimal risk. Oh, that is G. Risk of G. And so here it is according to P. Here is for all measures P plus epsilon. Should be smaller than that. So this is agnostic sample complexity.
Use bias optimal classifiers, the best this is the same thing.
The bias optimal.
Bias optimal, yes. And
Well, there might happen that there is no bias optimal classifier inside H. So here the best classifier is over all classifiers in H. So let us speak about risk decomposition. So this answers your question. Okay, so imagine that some learner algorithm. So here is 0, here is 1, and imagine, okay, that's 1 a bit higher. And imagine that this is the risk of our learned classifier. So then we will decompose it. Inside our problem, we can have irreducible risk. So this is the risk of bias optimal classifier. So H optimal is risk of bias optimal. Inherit a randomness like this 1/5 we have here. The second step is the risk of the best classifier. So this is the minimum, let's call it a G F star. So that's the minimal risk of F. So R F star is this minimum G and H of R of F. Okay. And this contribution is called bias. This is called irreducible risk. So I have a question to compute it in the quiz in the end. And this is called estimation error. So, for example, imagine that we learn threshold classifiers in this example. So what will be the bias for threshold classifiers? It's 0. Ah, yes, so good point. Yeah. Yeah, so we predict 1 here. So let's flip it then. That example, let's flip it to here. Now, what is irreducible risk of?
but I said 0 because I just don't see the difference between bias optimal and risk classifier in
Yeah. So there might be no bias optimal classifier inside the hypothesis class. So here F star is defined by this equation. It's just
okay. And
minimal risk.
you ask us
Yeah.
the H is a set of threshold classifiers.
Yeah.
Okay.
So labels are 0, 1, 0.
Yeah, for bias optimal, we need 0, 1, 0.
We don't.
We don't have it. And,
So-
yeah. So what's the best threshold
Zero,
classifier?
one, one.
Yeah, 0, 1, 1 works, or
Zero,
0,
zero.
0, 0, it's equal.
Mhm.
And so what is the bias?
To 150.
1/5. So irreducible risk 1/5, bias 1/5.
Mhm.
But then the learner algorithm might output might be a little bit wrong, might be a little bit away, and that's the estimation error. So if he only starts predicting one, okay, here it's a bit difficult, but okay, yeah. Okay, so this is all introductory things. Now, second thing is I will speak about finite hypothesis classes. And then I will prove something with VC dimension. Then we're finished for today. Okay. So, basically, we can think about cross validation. You want to fit some parameter, and then so what you do is you take a part of the training set, you use it as validation set, and then you want to get it for the optimal parameter. You use validation set and you take the minimum error on the validation set. So let's talk a little bit about this problem. Now, so imagine that we fix a function f. How can we bound the difference between true risk and empirical risk for a fixed function f? So we in advance we fix a function and we want to estimate its correctness on training set. So we estimate its error on the training set. And so then we can use Chernoff bound for this.
So the key difference.
Well, actually Chernoff bound because it's binary variable.
So the key difference between what we call true risk and the empirical risk is probability measure. So we need
Yeah.
to somehow estimate the difference that we gain when we change true measure to empirical one.
Yeah, exactly. So that we need to understand in order to know that we are overfitting. So when the yeah, and so we can bound it with Chernoff bound, and let me just write it. I mean, it's so easy, but if I do it from head, sure I will make somewhere a stupid mistake. And so I explain this. Yeah. So we can get the risk bound, but risk bound is just a bound on the risk of all classifier of a classifier that's produced by learning algorithm, or a bound on risk of all classifiers, and that holds for all classifiers of H. I mean, the bound can depend on the classifier, but I mean, just a formula that holds for. So if we fix F, and then we generate some set, then we know that F is at most RS hat of F plus square root of, and then what should be here? Okay. I want to prove it in the term of a written bound, so I need to say precisely what fix F with probability 1 minus delta over S over Pn. We have that Rp of F is bounded by empirical risk of F plus square root 1 over 2n ln 1 over delta. Okay, so how do we get it from Chernoff bound? Oh, I should have at least kept it here. And so here we have a probability 1 over n. It's b1 plus n is smaller than expected value of this. Let's say z1. Let's assume the expected value plus epsilon, and this is exponent minus 2 epsilon squared. So this is Huffing bound. I assume that,
you should have minus epsilon.
yes,
No, minus epsilon here, because it's the
yeah,
it's right
I
side.
want, not too far above. Yeah, you're right. I need to have the other one.
Okay.
So this is having inequality. So Z1 until Zn are IID, identical and independent in 0, 1 interval.
And maybe we should have plus X. No, because
No. I mean, here I'm saying this thing is not too much below the average.
okay, but maybe you need
So
one minus exponent.
Here I'm saying that if error on test set is good, then true error is also
Yeah,
good.
but I understand, but maybe you need one minus exponent because this probability approaches one when n approaches infinity.
You put minus epsilon and plus epsilon.
Yeah, but I
plus
say
epsilon.
greater than.
Okay, but
Yeah.
one minus exponent.
This is satisfied with high probability because you say that. So
Yes, this is just by a law of large numbers.
Okay, yeah. You're right. Of course. Sorry, yeah. Yeah, okay, yeah. I want, the opposite of this. The bad thing happens, yeah. So bad thing here. Yeah, good point. Okay, so I don't need to explain the details anymore. So it's very good. Okay, now imagine that this is for a fixed f, but now we're working towards bounds that hold for all h simultaneously. And so we can get a slightly weaker bound if we combine this with union bound. Right, so if we want such an inequality to hold for all functions in some finite f, then our bound will be multiplied by the size of h. And so we get the same result, but delta, we just can apply this h size of h times, but delta decreased by size of h. And so this holds for all h. For all f and h. Okay, and we can go even further. So imagine that we are fitting decision trees, and we want to optimize the size of decision trees using such a risk bound. So we know that we have a nice formula for the size of decision trees with k leaves. And so now we want a bound that holds simultaneously for h1, h2, and so on. Decision trees. For example, decision trees with k leaves. So we want to apply this bound for several sets differently, and we do it by assigning a weight to each set, weights that sum up to 1, like we did before. So we just set wk equal to 1 over k times k minus 1. And then we apply this, but for each classifier, we use delta times the weight of k divided by the size of hk. And then we get a risk bound that depends on the size of hk. And so we have complexity variance trade-off. And so the claim is that
doesn't this bound also depends on size of each decision tree.
so for you're right. So we get a bound that depends on the size of the decision trees. I want to speak about bias complexity trade-off now, like we did before. So for every k, so let us make a claim now. A similar lemma with the probability 1 minus delta over s and pn for all k, for all f in hk. We have that rp of f is bounded by our head s of f plus 1 over 2n, and then all the same things. So L and size of hk plus ln wk over delta. This is our lemma.
What is the?
So WK is this way to be assigned, sorry, I deleted it. It's 1 over K times K minus 1. But you can plug in any series that converges. So it's not so important. Usually this is much bigger. You can even choose W. And if you think about applications, you can even choose this one. Because this logarithm will anyway be much smaller than this. So you have huge freedom. But usually you want something that's polynomial, then this becomes logarithmic in K, and then for sure you can ignore it.
Again, why can we use this? So why can we use this WK? Why doesn't it grow?
Yeah. So now we have to apply union bound over, so we want to have a result for all K, for all F and HK. And so we will apply our bound here. Well, the original one for the fixed K, but instead of replacing delta by delta over size of H, we replace delta by delta times WK divided by size of HK. And then when we take the union bound, we have to add up all these probabilities. And so we just get an extra sum over WK, which converges to 1. So we get, essentially, we get the sum over WK delta times delta. And since all the W's sum up to 1, the error probabilities sum up to delta.
So we do a union bound on all decision trees of size K.
Yeah.
But you choose a smaller delta, but multiply by number of.
Yeah, I make it smaller by multiplying by this factor.
Okay.
Yeah. Okay, and so if we think again about decision trees. So when we think back about decision trees, this will be empirical risk. This will be ln, so with binary inputs, we had k times ln d plus 2, where d is the dimensional of the input. So we have bounded by square root 1 over 2n k times ln d plus 2 plus ln, and then like 2 ln k over delta is already more. So you see that the effect of these W's is just logarithmic. Also, ln 1 over delta is really small, and you don't care much how big is delta. You care a lot about value of epsilon, the square root, but delta, like people set it to 1/4 or even 1/2. It is the confidence that during training, the confidence that after training you get the desired result. And people just say, I am happy to put it equal to 1/2, because if I happen to see, if I'm unhappy about the result, I restart my training. It's a small effort, because usually training is done once by some data scientist. So he doesn't care about putting, but even if you set delta equal to 1 over 1,000, then this will be like, you have this factor in the term besides n. So you have something that goes down with 1 over square root n with this factor. And so even if you set delta equal to 1,000, you get 2 over square root n. So this contribution is really small. Like if you want to check a single function, then you can use this bound. That's the Hoeffding bound. Or in theoretical computer science, they say Chernoff bound, because they only care about binary variables. Almost always. So that's Chernoff bound, and here for similar reasons, all these things are really small compared to the size of the class, even for decision trees. Although in practice, such bounds, they are very far off. like there, and you need to have, there are some examples in the notes, I don't remember them, but you need like sets in the 100,000s to get something meaningful here. So to get something less than 5% in the square root. So yeah, so this is all theoretical observations. I mean, all this statistical learning theory business, it's not so convincing because the bounds are so loose. They're all in papers, there's always with big O notation. But to understand what is the best classifier, you need results without big O notation. So you need to get really close. So all of this is speculative, but there is nothing else. And at least, yeah. So just a failure on theoretical side. I mean, these papers are already difficult, even if they were written well. Okay, I should not criticize too much when I'm on the YouTube. Okay, so but just in the future, hopefully this thing, like this course almost got canceled 8 years ago. Nobody understood why it should be done. But now there is huge research group by Naumov, and it's a priority. Even though all these results that they are yeah, not enough to be convincing, but okay, humans will get clever and will get there. So I'm positive that.
So once again, we have their infinite sequence of
Of
classes of trees, and we now we consider that the true we don't have true classifier. So what is K?
So K K is the size of the decision trees. So when we happen to find a certain size for which the trade-off between error on training set and overfitting term is good, then we will have good error on the test set. This is what it means. And again, we have this like, but now it's a bit more complicated curve. So for online prediction, we had kind of a linear overfitting term. Now we have square root, like this is our overfitting term. So this is a square root term. And here is our head S. And so these, and the total, so the sum of these two will be something like this. Square root of 1. So here is a square root term. So here I'm plotting this bound. It is the sum of two things. Empirical risk. So this curve is our head S. And this curve is the square root term. And then the risk bound is the sum of these two, which is, okay, it's a bad drawing, but you got it. It will have like some, I evaluated a few times, and I must admit that this minimum is not so convincing when I plot it. But okay, here is a theory, here is a sweet spot.
And on axis, we have the size of the.
Yeah, sorry. Size of here is
So we plot this to find the best decision tree size, depending on the test or the training test size. Okay.
Yeah.
And this gives why our head is looks like linear.
Well, okay, I just draw something. It's,
okay.
It's
So
probably
it's
not
just,
linear, but
it just drops down.
Yeah, initially it drops fast and then it starts to drop slower. And for large K, it will be 0 because you can fit all classifiers if the trees are big enough.
Okay.
And so this is bias complexity trade-off. And in machine learning, they speak about bias variance trade-off because they have slightly different formulas, but it's the same idea. So there, the variance is variance in of the classifier. They say that when we change S probabilistically, then F changes probabilistically, and if the model complexity is large, then the difference between various classifiers is very unstable. But if the model is small, you will each time get the same classifier. But this makes sense for linear regression, at least for polynomial regression or so. But so I say bias complexity trade-off, like in the books, because It's more general, like we don't know what's inside H, and H, the learned classifier can always be very different. So the notion of variance is a bit strange here.
And one more question.
Yeah,
Do we fix K and then apply all those bounds and everything? Or you do it?
no, it holds for all K simultaneously.
Ah, okay.
So with probability 1 minus that over C, we get this for all K. But I mean, if we do it for fixed K or not, it's just logarithmic term here, so it doesn't matter much. Yeah,
But if we do it for all K, then our S isn't zero.
so what I'm saying is that the bound is valid simultaneously for all K. But here in this formula, I optimize, so I look, so here I assume that F is an HK.
Ah, okay, okay.
Yeah.
Well, okay, we've been discussing a long time, but it's not a problem because things are rather smooth. I just need to tell. So the last thing. Okay, I will skip this minimal description and because we covered this. And so now I just need the last 3 pages to explain
The proof of this result. So that says that any classifier that minimizes empirical risk, error on training set, will give us an optimal classifier here. And this can be used to prove that agnostic sample complexity is proportional to VC dimension. So I will, at the end of the lecture, I will put a big theorem that combines everything from the last 3 lectures, the main result. And some people call it fundamental theory of statistical learning theory. So there are 2 popular books that call it like this. So everyone starts to use this name. Okay. Yes, I need to prove this one. Okay, and so there is this story that risk bounds that can be used to fit hyperparameters like the size of decision trees without wasting data on a validation set. When you take a part of the input set and use it as validate, this data is not used to improve your model, so it's kind of wasteful. So that's a first reason why not to use validation set. And second reason is computational. Like if you have many hyperparameters, like in a neural network, you're optimizing the number of nodes in every layer and the type and whatever thing. Then you have many hyperparameters. So there is no chance to try all hyperparameters for computational reasons, because if you have 5 parameters that can have each 10 values, you have to check 100,000 things. It's banned. So what you want to do is for each number of mistakes, optimize such a bound, choose the best parameters. And then you just have to retrain for each step of this value. So sometimes you can be lucky. You can have an algorithm that says, okay, if the error is so much, find a model that optimizes these hyperparameters. And then you have a guarantee on the test set without using validation set. Okay.
It looks like aggregating information to data from statistics.
Yeah. There are variants everywhere like this, but this is kind of like 2 reasons to think about it. And I speak about this because this proof works like cross validation. So we will now generate a new set and treat it as a validation set. And then, as usual, we will like randomly scramble the test set and validation set, and then see that error on test set and this validation set is likely to be similar. It's precisely the same as previous lecture. And so we can get this proof, but now in agnostic setting. So in agnostic setting, it's more difficult. So we have sample complexity is proportional to VC dimension squared in agnostic setting. So first, in realizable setting, so sample complexity is smaller than in the agnostic setting. I forgot to tell this. So Yeah, it's okay, fortunately, yeah. So realizable setting is a special case of agnostic setting when this measure P over XY is deterministic in Y. Once you fix X, then the true label must be of measure must be concentrated on the true label. So conditional measure is concentrated. So then these two models become equivalent. So the probability of having a mistake will become equal to the risk. Yeah, okay, so so all these bounds, they hold for all measures over P. So here is actually the quantifier over P, all P. So all a result in realizable setting, they start with the quantifier over the measures. And here we have also always a quantifier over the measures. But in realizable setting, we also fix a measure over inputs and a true function. Here they're coded together. And so every problem determined only by a P here corresponds to a measure over inputs in a realizable setting. Sorry, I need to say that. Okay, we start with the measure. So realizable. So we have measure P over X and H inside H. An agnostic setting. We have P over X times Y. So in realizable setting, our theorem needs to hold for every problem here, and the problem is measure over X and H. And here a problem is just a measure over pairs. So how do we go from okay, let's call this Q now. So how do we go from such a problem to such a problem? We choose Q to have marginal measure equal to P, and conditional measure is concentrated on H of X. So so it is kind of statistical thing. So we say that marginal measure. So if we have a marginal measure and a conditional measure, then we have a joint measure, right? So marginal measure Q is equal to P. So marginal measure on inputs. And conditional measure so Q Y given X is equal to 1 if Y is equal to H of X and 0 otherwise. So now it's clear, okay? Yeah. So let us go through the proof, because now 20 minutes left. Starting to get a bit. Oh, and we need to do the quiz. So first, I will speak about other concentration inequality. So remember that before we had an urn with even number of objects, and all are marked. Even number of objects. And so we will take a random half of objects out of the urn. So we throw away random half. And K is number of marked objects that are left. And now we want to say that K is close to L over 2. And so note that K doesn't have binomial distribution. So that's good if you agree, because that's another 15 minutes saved. I mean, some years there was a fight over it, and you can just check it. If you have 4 objects and two marked objects, then the probabilities will be 1, 6, 4, 6, and 1, 6, not 1, 2, 1, 4.
Okay, so it means we cannot apply Chernoff bound or Hutling bound. I mean, with the original proof. But if you look to the proof of Chernoff bound, if you do it carefully, you can replace some probabilities by conditional probabilities. Because in this problem, like let's take the objects, let's throw them away one by one. If for some reason you throw away many marked objects, then you're more likely in the next step to throw away non-marked objects. And opposite, if you throw away only non-marked objects, you will become more likely. And that means that conditional probabilities go in your favor. So it's not surprising if you go through the proof. Yeah, it's more, but it's kind of tricky because if the tails are smaller, that means that the middle is higher. But if the middle is higher, if you're too close to the middle, no, it doesn't make sense for them. Okay, forget about it. Yeah. So, but at least what we have here is, but by the way, next lesson we will learn a more general measure concentration bound, and there we get the proof without like directly from the statement of the general result. It's bounded difference inequality, it's called. And there is also even more general Azuma's inequality. I don't know if it was in your course. No. Okay. Yes. So I want to say that lemma probability that K over L is 1/2 minus epsilon is bounded by exponent
less than 1/2.
Yeah. Minus 2 of the square the lemma, and we will use this one. But first we need to make a cross validation bound. So we want to prove this, and we will replace this by generating test set and looking at the number of errors on the test set. So here we have to, what we will do is we will set this equal to epsilon, or better, let's I will set this equal to epsilon and then calculate some probability that something bad happens. And then I will substitute this epsilon and verify that whatever bad thing happens is smaller than delta. So delta appears here. Okay, so our first step is to say, I will write it in the bottom, the structure of the proof. So I say that the probability that this is violated, so probability that RP of F, we need to put existing symbol here. Probability that there exists F in H, such that RP of F is bigger than R hat S of F plus epsilon 1/2 smaller than probability. And now we generate a train and a test set that there exists F and H such that, and now the natural thing. So I replace this by the error, the fraction of error on the training set, F bigger than R hat S of F plus epsilon. So the probability increases a little bit by factor 2. And this follows from Chernoff bound. And then I will I will prove that this is bounded by a growth function of h of 2n times exponent minus epsilon squared and 2 times epsilon squared. So the second step will be a consequence of this lemma. So that's, we just have to understand these two inequalities, and then we are done.
Well, okay, we need to remember the bound from last time. So we also use that GH of n is smaller than En over D to the power D, where D is VC dimension. So D is VC of H.
So once again, what's the GH? What is it?
It's the growth function. So if we restrict the function to endpoints, how many different behaviors can we have on this endpoints when we apply functions of H? Well, it's from previous lecture and we proved this bound. So we substitute it in here, we get this inequality. And then what we get here, we prove that it's smaller than delta. So this is a computation. After we are here, we are done there. I skipped computation because it's just boring. So after we get here, what do we have? We have an expression. So there is that depends on epsilon n, and of course VC dimension is fixed. Okay, then we substitute value of epsilon, which I defined there. And then we verify whatever is left is smaller than delta. It's terrible, yes. I agree. Well, there is only one epsilon here, so it's that little less terrible than our previous.
And what do you get after your computation here?
Yeah, then you get something smaller than delta.
Okay, so I can write.
Okay, I can write smaller than delta
Okay.
here. And then we see that this probability is smaller than delta. It's precisely what we need to prove. With probability at least 1 minus delta, we have that this holds. And
what
here
epsilon-
is
what epsilon do we use?
here is epsilon.
Okay.
Without the 3, but because I start with 3, I start with 3 epsilon here. And here should be 2 epsilon. Okay. So do you agree that we have 2 tasks, prove this inequality and this inequality? Okay. So let's start with left inequality. Because it's easy one. Okay, let us look to indicator function of sorry, I need to prove. Let's look at indicator function of
What's the difference between RT and RT?
RT and RP. Well, here we generate 2 sets. T is a test set or validation set.
Okay.
So we generate 2 sets according to Pn here.
And here I have
Yeah, only 1 set here. No.
okay.
Now we will prove this one. And so we will fix S and let F star maximize this difference. P of F minus R hat S. And so now this is just a fixed function. Okay. Oh, let us look to 1/2 of indicator function that RP of F is bigger than R hat S of F plus 3 epsilon. Okay. So this is indicator function. It's either true or false. And okay, I forgot to put it, so I need to have a look. And here we have, let us prove that this is smaller than probability over T. of Pn R hat T of F star. I forgot the stars here. Bigger than RS hat of F star. Okay, so what is written here, probability for random tests, recall S is fixed, so here is a fixed value. When we take a training set, let's look to probability that this is true plus 2 epsilon. Okay, so how can we prove this inequality? So let's start. If F star fails to satisfy this condition, then we are done. But if F star satisfies this condition, then we know that RP will be close to RT by Chebyshev inequality. So this first step will hold provided that n is at least 2 over epsilon squared. If this is not true, then inequality is easy.
Then we have something like triangle input.
Yeah. So if n is large enough, then Chebyshev will say, so we need to check the variance. So we have a list of n binary variables. Variance of one binary variable is 1/4. So Chebyshev will say that probability of RT hat of F star minus RP of F star smaller than epsilon is bounded by, and what should I write here? Variance, which is 1/4 of this thing. It's the average.
Divided by n
Epsilon squared. Yeah, Chebyshev has the
okay.
and then we apply this bound here. I say assume this thing here.
And now RP is close to RT.
Yeah.
Okay.
Yeah, so then this will be smaller than 1/2. So with probability 1/2, we will be close. And so, yeah, here comes 1/2 and we are good. So this probability is 1/2 and then we are true. Indicator function is at most 1/2.
Can you repeat please about inequality, why we get variance 1 over?
Oh, sorry. Also, I did again in the wrong direction. It's been known, it's binary variable. So it's true for all binary variables. So the variance for
B times 1 minus B.
yeah, 1 minus B is optimized to be 1/4.
It's maximum when B is 1.
Yeah. Okay, then so we have proven this inequality. Now, well, the 1/2 is just the other case, one of the 2 cases. So this is always true. Then because either this is 0 or this is 1, and then if it's 1, we get there 1/2. Okay, so now we take expected value over this thing for S. So here S is fixed. And F star is just the one that maximizes the difference. So this maximization takes care of this exist of F of H. And so we take expected value over S. And then this inequality is trivially true.
Okay. But
yeah, because if we use the existence here, then this value can only increase. So I need to optimize this bound. Okay, I think it works. So this is done. And now our last task for today is to prove this bound. 2 minutes left. Okay, so now what do we have here? We have a test set and a training set and a test set. And we can do the same thing as before. We can generate a set of letter size 2n and randomly permute them. And then we will think about this analogy. So there are two cases. First, let us assume that, okay, what are marked objects? Marked objects are balls for which this f makes, so let us fix them. So here there exists f and h. Let's now pretend a special case. H has only one function and prove this inequality in this case. Okay, h has only one function. Then what will be the balls in this case? Marked balls are balls for which this one function is wrong, makes a wrong prediction. Okay, now let us assume that number of marked balls is smaller than n. Note that and there are 2n balls here. So even number of balls equals their amount is 2n. Okay, then it means that what do we have here? That probability that marked balls in the half is smaller than 1/2 minus something is exponent this thing.
Maybe n over 2, because you have n marked balls.
Yeah, well, we need to work a little bit on this equation. So let me write it. So we have 1 equal to 1/2 minus epsilon. Let us multiply it by 2 L over n on both sides. So we have 2 L and k here, and this becomes 2 times 1/2. So this falls out, L over n minus 2L over n alpha. Okay, and so so what does it mean? That it's just something small technical. The problem is that here we have L, we want to replace it by n. So to get from here to here for one function, we just have to choose alpha. And so let us check whether we can take alpha equal to well, but first I want to rewrite this thing here. So we will have kn smaller than 1 minus k over n. So we have here 2k over n, so 1 I bring to the other side. Minus and then something. Okay, we can call it epsilon. Add 2 epsilon. So here we choose not this, but epsilon equals 2 alpha times L over n. That's how we apply it. Okay, where am I? Yeah, here I am. Okay, and then we are good, right? Because here k over n, k is marked balls, will be a fraction of balls in our test set. Or sorry, let's take our train set. So we set 2 epsilon to the other side. And then we are good. Yeah, that doesn't matter. Like, so this is RS. Okay. and then RS plus 2 epsilon, and this is RT. The balls in the half that we throw away. So then we understand that this probability is at most, okay, if H is singleton, this is a 1, exponent of this thing. Okay, because we apply the lemma. And now there is the last step. What if H does not contain a single function? So we do again the same thing. So we say we fix a union of S and T, we call it U. So note that in the proof of this inequality, we could fix a union of S of T, and then we've been randomly splitting them. Right? So when we fix the union of S and T, then we only need to apply the union bound. And so the naive way would give us size of H here. But after we fix union of S and T and then randomly split it, we can fix this union.
Okay.
And we need union bound. Yeah, only the different behaviors over this union. And this is magical trick to prove something for infinite H. And this will be the factor from the union bound. And so we have proven the second inequality. And that means after we plug in value of epsilon, work it out, we will end up with delta. And simplify it a little bit. And that means we've proved this theorem.
Okay.
Okay, so that's when we finished the lecture. So now it's time for quiz, a prepared quiz. So, but that means you will be a bit late for your next lecture. Then come on. Oh, these computer is not ready. Okay, I will first stop Zoom. Okay, I will put. I think I should stop Zoom because my computer is crashing. But I will restart Zoom in a minute. But just